nothing is done by accident. Okay, there's no way to test you on everything. All right, and that is why, see, the mentality of students everywhere is that you study topics A, B, C, D, and you are to be tested on A, B, C, D. Well, on the final, expect to be tested on points that I did not cover in class, but they are parallel to what I'm doing in class. Expect that.
What do you mean parallel?
So if I talk about, for example, a topic, if I cover a topic, this is an advanced class, and I expect you to read more than what I'm doing in class
Yeah, so like
on that topic. I'm sorry?
Like the textbook is like our base, right? Like that's
That's right.
Okay.
Yes, exactly. It's in the reading material, but I just have not spent as much time on it. There are many other topics. Yeah, I understand your point, because I once took a multiple choice test and 75 questions, and all the answers were C.
Yeah.
And I freaked out. After you put 20 C's, then you say, well, something is wrong. Well, so I understand all the points, and I want you to I'm open-minded. Is that a perfect test? No, it doesn't exist. But I tried to warn you with, I did, with what to expect. The bottom line is I expect people to study very hard. That's it. All right. I use the same policy with my own kids. In fact, I make it very tough for them, because I want them in real life. I want them to be ready, and this is what I am trying to do. Okay, so there will be no quiz, as I mentioned, this Thursday again. I sent you an email. All right, read your emails. But we'll have a quiz unless something changes every single Thursday after that.
Okay, and then is the homework would be next Thursday, not this Thursday?
Homework 6 is assigned today,
Okay, it's assigned today.
and it will be due next Thursday.
Okay, with the quiz.
That's right.
Okay. Yep.
Okay?
Homework 5 is due today, right?
Yeah, I mean, yeah, you have the answer, so you can just put it up over there, right?
Cool.
Homework 5, okay. And I gave you, I think, a pretty good bonus, and so I try to help you guys out, but I want you to work very hard for your benefit. Okay. And there were a number of people after the bonus that went over 1,000. That extra, if you got that, that extra credit or bonus, whatever, will count. It will pile up to the total number of points for the whole course. Okay? And I will also drop the lowest quiz. So, I mean, I'm trying to help you guys out. What?
Will there be more events that improve extra credit?
I also send you an email. If you come to those things, you're going to get... I don't know at this point. Okay. But, I want to see people working hard. That's the bottom line, okay? This is an advanced course. It actually should be in the 4,000 series. The only reason it's not, I was told by somebody, is that because they have to have a certain limit of 4,000, some other administrative things that I don't know. Okay, so, and here are the topics to study for the final. Anywhere you see a discussion about Excel minor, take it out. I mean, ignore it, skip it. And I'm trying to, I could make it easy by not using jump, by using what I was using before, but I challenge myself to try to give you, to learn a package, jump, which is a very good package, so that you guys can get better jobs, and the computer is slow. So, we talked about multiple linear regression a little bit. Today, I will I will review the concept of linear regression and multiple linear regression. It's a part of it will be a review. So this is where we are. Multiple linear regression. It's supervised learning predictive. Okay, and we will be on it today and Thursday. And this computer should be flying, but it's not. And I also the Artificial Intelligence Institute, there was a big article on the Northeastern website. Find out what's going on with it, get involved. You will benefit from it. And it's great that the school does it. Do not wait for somebody to ask you to be involved. Okay, so I have a bunch of things here, and I'm all right. So the document I want to start with is this DM Week 7 multiple docs, and that includes the PowerPoint slides below. So let's talk about the concepts. And let me see if I can put this in OneNote. Okay, so in the beginning it starts with Excel minor, so skip all that stuff, all right? And so on this document, I will, the first place that stop it. These are slides from the book. It's from the previous edition, but the same the same things apply today. So basically, I went to whatever page this is, 27. All right. So this is I'm going to use the chapter 6 Merley slides. All right. Multiple linear regression. We have two types of multiple linear regression. One is called explanatory, and the other one is called predictive. When you take statistics in a traditional statistics course, we study explanatory statistics. I'll explain what that is. And in data mining, we do predictive multiple linear regression. And I am going to be using a few different examples. The example that is used in the book uses it's a file called Toyota Corolla, and I have a jump file. There's a Toyota Corolla, there's a Toyota Corolla 1000. This has 1000 records. The other one has, I don't know, 1300, something like that. I'm going to be using the 1000 record version. It's a whole number. Okay, that's it. want to be able to annotate, and that's why. Let's see. So we'll be using that file to demo things. It's one of the files that I will be using. From this point onward, the concepts we studied regarding confusion matrices, the error metrics like RMSE, root mean square error, will be used frequently. We'll talk about lift. I'll be mentioning ROC. So we'll be using most of these concepts, if not all of them. Now, in statistics, when we study the explanatory multiple linear regression, we worry about how close the dots are to the line. Okay, so this is called goodness of fit. So, all right. So, they keep re-imaging the computer. So if I in explanatory multiple linear regression, okay, you have the your observations like that, and then you okay, in two-dimensional, okay, this is simple linear regression. Explanatory means you worry about how close these dots are, these observations are to the line. So how good this line is, how well this line fits the data. That's what we study in explanatory multiple linear regression, in explanatory regression. The problem with that is that if you try to predict, so here you have x values, okay, here you have x values. So you have, and I'm going to go over this, you find an equation like this, 3x plus 2, okay? What you want and what we want to do, we want to be able to predict. So if x is a value, right, if x is 10, what is y, right? And this is really y hat, right, from the sample data. The problem in this is the following. Let's say that the minimum value of x here is 2, and the maximum value of x is 19, all right? You see, we do a very good job in predicting y, and let's say that this is the price of a house, all right? This is the price of a house, and let's say that this is the square footage, okay? This is the square footage. So the price, let's say, so x is the square footage, y is the price of a house. As long as x is between the minimum value and the maximum value, we can predict, right? If x between, we can predict y hat, right? Just put in the value of x here. What happens if x is greater than 19 or smaller than 2? The explanatory version of regression does not handle that and cannot handle that. But this is what we want. And so, and that is why Oh, very good. And that is why we want to do don't tell me, I should be able to view. And that is why we go to predictive. So, with explanatory, the emphasis is the goodness of it, how well the line fits the observations. In predictive, we care about how well we predict, how accurately we predict as the price of, how well we predict the dependent variable, okay? So it's good to know beforehand why we are doing regression. And we are talking about linear regression exclusively here, because there are other types of regression, nonlinear regression, logistic regression. We will see logistic regression later on. Now, we have okay, well, all right. Anytime we have supervised learning, remember we have training data, we have validation data, and test data. And then we have new data. The training data, as we discussed, is used to train the software to create a model. The validation data, or another word for validation data is holdout data, because you're holding it out so that you can test the model. And and then if we have test data, we can validate once again, and with the training, with the validation, with the test data, and with the new data, you see in the beginning, training, validation, and test, these are all in one file. You just break up the file into training, validation, and test. So the training, validation, and test, they all come in one big file. They all come together. You can, once you become very good with these things, you can start to improvise. New data is data that comes, let's say, next week, okay, that has not been seen at all. When you do multiple linear regression, there are certain conditions that, certain assumptions that need to be satisfied. Some of them can be loose, so loosely satisfied. When we have the actual data that I described here, all right, okay, like this point right here. So this is a point, let's say, xi, comma, yi. So yi, this is the actual, the observations are the actual data. And the point here on the line, so this is that point. This point right here is the point xi, okay, comma, yi hat. All right? I mean, this could be the point 510, this could be, so if you have an actual observation, here is xi, right? In the beginning, you have xi, yi, right? So you may have the point 5,10, y I had would be, you take 5, you plug it here, it would be 17, all right? So the error, right, the ith error in this case would be actual minus predicted or forecasted, right? So the error here would be -7, all right? Actual minus predicted. And many times instead of yi, we use actual. Instead of yi had, we use f for predicted or forecasted, right? So the assumptions are that this epsilon, this is called the error or noise. This error, we assume that, or we would like it to follow a normal distribution. That means that if I if I took all these epsilons and I did a histogram, okay, this is what it means for data to be normally distributed, right? If you did a histogram, a frequency histogram, right, and then you approximated that histogram with a smooth curve, that smooth curve would be as close to this bell-shaped normal distribution curve as possible. So this line here would be called epsilon, all right? We would assume that another assumption, these are very important assumptions. So yes, we are talking statistics right now. I'm reviewing stuff, and I told you where to go and read that. There's a document online. It has a whole chapter. You are responsible for knowing that. So the what was I talking about? Oh, the linear. Remember that we have two kinds of variables. We have independent variables, and we have one dependent variable. Okay, one dependent variable. Now here you have many independent variables, and here you have the one dependent. You always and you only have one dependent. So this could be x1, x2, x3. Now, there are relationships between these, x1 relating to x2, x1 relating to x3, x2 related to x3, and then the relationships between independent, each of the independent and the dependent. Okay? When you are looking at the relationships between independent only, you do not want a high, you don't want a high correlation between them. But when you, so in other words, if the if I take x1 and x2 and I find the correlation coefficient R between them, all right, and if that is high, that means, so if this is if R is, if the absolute value of this is close to 1, you want to eliminate one of the two. We talked about that. But what we want, if you take and each of these independent variables, right, and you see how it relates to y, we want these to be highly correlated. So you want to, these are independent variables that have to do, that are closely related to y. So if y is the price of a house, right, x1 could be the square footage. You want to have something that is related to this. I mean, if x is the number of dogs owned by the owner of the house, then you don't want that. That has nothing to do with the house price. All right? So you want independent variables that are not highly correlated to each other, but you want independent variables that are highly correlated with the dependent variable, the variable that we're trying to predict. By the way, are you guys watching the videos that are posted online? Okay, question?
Yeah, if you have multiple independent variables that are correlated with the dependent variable, wouldn't those be correlated as well?
Not necessarily, because square footage is one factor that affects the price of the house, right? What about number of bedrooms? Now, that may be, that may happen, but not necessarily. If you have the most important knowledge when you're working with independent variables, that's a very good question, by the way, and dependent variable is domain knowledge, knowing your environment. For example, you may have a big house with small bedrooms or a small house with big bedrooms, whatever. Having a high correlation does not mean causation. So just because you have, for example, square footage and the number of bedrooms, you can say, well, it makes sense. The more square footage you have, the more bedrooms you will have. Well, that may be a high correlation there, but that is not necessarily a causation. One doesn't cause the other, all right? Anytime you have high correlation, you always have to think, does that imply causation? Because it may or may not be. So, but just because you have x1, x2, x3 related to y, it does not necessarily mean that x1 will be highly correlated to x2. Okay? But this is something to keep in mind. If you have knowledge that this is potentially, that this can happen, then you want to look into it further. Okay? A good point. All right. So domain knowledge, where's my dot? Okay. So when it says the linear relationship is correct, this is each independent variable related to y. The cases are independent of each other. Each observation is independent of the other. These are the assumptions. Can't find this thing. Hello. All right. And that the variance is consistent for many different values of x. These are assumptions. We're not going to go into too much detail. I wish we had the time, but in the stats class, those were mentioned as well. So just know the assumptions right now. We assume that the errors are normally distributed with a mean of 0 and standard deviation of 1, and the error, we call it noise. Noise, missing data is a noise. Invalid data is a noise. Extra characters in your data set is a noise. Noise is anything that disrupts what you're trying to do. Okay, so the explanatory modeling is what we study in statistics. The goal is to find the goodness of fit between the independent variables and the line. Okay, and we look at R square. Residual analysis studies the residuals, the errors. Another word for error is residual. And you will see how we're going to be using p-values. Predictive modeling, here's the goal. Very, 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 very clear, very precise. By the way, what I recommend that you do is you print these documents, especially after I've gone over a document, print it out, and things that you don't understand, put question marks on them, and come with the document and say, these are my questions. I mean, if you see me sometimes, many times, I like to, if the weather is nice, I like to be outside. If you see me out sitting outside, unless I'm doing something, right, stop me and come and ask me. It doesn't have to be office hours. All right? So, here we're trying to predict, and this is what we want to do in this class. All right? And we have ways to assess the performance. And usually we use validation data for it. Why do we use validation data to assess the performance of an algorithm and not the training? You guys already answered that before, because the training, the metrics like RMSE, average, whatever, those are going to be much lower with the training data than with the validation data. Okay? Multiple linear regression is used extensively, and in real life, you can have thousands of independent variables. So, we have this Toyota dealership, and they what they're doing is they are allowing you to trade cars, and this is a technique that many dealerships use. You can trade in your car so that they can get you to buy a new car, and all they want to do is to maybe break even with the trade-in, whatever profit they make for that, but obviously they want to maximize that, and they want to be able to predict the price for the used cars that they're buying, the dealership, right? They want to know if it's a Dodge, and now it's 2019, it's 2012, you know, the blue book. They try to predict what is a price, an advantageous price for us, the dealership, to offer to the person who wants to buy one of our Toyotas, so that we can make a small profit. So these are the columns here. All right. This is what is very important. I love dealing with data, and whenever I get a data file, this is what I recommend that you do. Try to learn as much as you can about this. So you have the price, the age in months. This may be the car, okay? The kilometers that the car has, the fuel type, and you have different types. You have petrol, diesel, CNG. The horsepower of the car, if it's metallic color, yes or no. If it's automatic, yes or no. So these are the dummy variables here, right? 1 and 2, this categorical data. Another categorical data is the fuel type. You have these 3 different types. Cylinder volume, number of doors, quarterly road tax in euros, the weight in kilograms of the car. This is, it's very important to know this before you get started. Do not start doing any coding unless you understand this data. And I was teaching these concepts, and at the same time, because of time pressure, I was not following my own advice. It took me 10 years to put my foot down and told people that gave me data, unless I understand your data, I will not do any programming. And they told me, what? I said, yes. They had given, there was one big project that was given to a number of people, and every single person that started that project failed. And I said, that is why the previous people before me failed. And I told them, I will succeed. I will not do anything for a month until I understand. I give myself a month. And I said, when is this project due? They told me 6 months ago. They lost hundreds of thousands of dollars. And I told them, the reason that you lost money is because those people did not understand the data. I'm going to do it properly. I put my reputation on the line. They did not believe. Then they told me, we didn't believe that you're going to do it. So they had plan A was to go with what I was going to do, and plan B was to do it manually like they used to. Okay, but I delivered, I did the whole thing. And then you want to also collect metadata. For example, price. What is the minimum and the maximum? The age of the car in months. Well, if it's over 3 years old, can I get some information about what happened to the car? You know, now it became, I think, almost a law that the CarMax, whatever, the Carfax, to try to get information about the car. So you try to get more more data about this data, and that's called metadata. Okay? See, when I give you a term like that, metadata, right? And that's why it's important to watch the videos. Take a nice frappuccino, sit down, put your feet up, and watch the video, and pause it, and go back. So, all right. So if I just mentioned the term metadata. Well, I want you to learn what that is, spend a little bit extra time, learn more about it, because I can give you a question on metadata. Explain what metadata is. That is what I'm talking about on testing you on things that I don't spend too much time in class. You've been told. Okay.
Sorry, could you say what metadata is again?
Metadata is data about data. So basically, the fuel type, right? The fuel type, we have 3 different types of fuel: petrol, diesel, and CNG. What does CNG stand for, right? Cryo
Compressed natural gas.
natural gas, right? And I work for a utility company, I forgot. So if I, metadata is, okay, this is categorical data. And if I want to use this column in my calculations, I would have to do what to it?
Make it 2 binary.
Exactly. So initially I will make 3, right? But then I will keep 2 because that's all I need. And in fact, we will do that here. So I have an Excel file that I'm going to cover, let's see. And you see where I said Toyota Corolla MLR backwards method, replace this with jump. I'm going to show this to you with jump. Oh, okay. This, well, I'm gonna do this next time. I am going to show you, I'm going to walk through this Toyota Corolla file and use jump to illustrate the concepts. So here is a sample of the data. Okay. Now you see here fuel type has, it's going to have 3 distinct values. And metallic has actually 2 values, right? One is has metallic color, 0 it doesn't. Automatic, 1 means it's automatic car, 0 means it's not. So what jump does, by the way, even if you try to use this the way it is, it will break this down and it will dummify it. It will create dummy variables, right? So here are the variables. Now, very important. I would say that 60 to 70% of all work done in analytics is cleaning up the data, prepare the data so that it is ready to be data mined, it is ready to do forecasting, it is ready to do AI. We are doing AI. AI, the great thing about AI is a potpourri. It's a combination of many disciplines. Okay? And it's a fantastic field. I mean, I'm in love with AI. I love it, and you can, if you love to be challenged, AI will provide that opportunity. Some of you can go into healthcare, the healthcare component. Somebody else may want to go into the engineering. It's omnipotent, meaning everywhere. Okay, and as I keep repeating, you can start a company with $0.0 investment. You have a concept, you sit down, you work hard, and you can do very well. The worst thing that can happen when you have an idea and it doesn't work is that you will have learned the steps, and you can use it the second time to be more and be more focused, more careful. So here you have a bunch of different columns, right? As you see, the units here are quite different. when the dimensions, when the columns are in different units, that is a good idea. This is a good time to standardize. Okay? You normalize by standardizing. And how do you standardize any one of them? If x is the price, x minus mu over sigma of x. And you produce the z-score. See, I just mentioned the z-score. I expect you to know what that is. I am making your life difficult now so that it is easier later on. I expect you to become researchers of the concepts that I cover in class. Okay, z-score, we talked about it. Find out what it is, because I can test you on it. That is the kind of a thing that I expect you to do. I think of you as being close to in some ways, a researcher, right? Because that's what this field is. I mean, you can't say just do 5 things and that's it. Everything is tied to everything else. All right? Last night, the Business Analytics Club had a presentation on forecasting, and we had students from industrial engineering, from computer science, from the business school, okay? And because when you say forecasting, when you say data mining, forecasting is one type of data mining. It's not tied to a specific discipline. People from entrepreneurship here, from our business school, was anybody there last night from here? Okay. All right. So these are the columns, and when they have different units, then you want to, that is one situation where you want to normalize. The weight is in kilograms, right? in kilos. So here, right, you have a car, and it may be 5,000 kilos or 5,000 pounds. If I use the weight together with the doors, you see the doors, you have, 2, 3, 4 doors, 1, 2, 3, 4. If I use numbers from the doors column and numbers from the weight, the statistics, whatever statistics I come up with, they will be overwhelmed by the weight. So you can say the average of doors plus weight is 2,500, right? It doesn't make sense. But when you standardize them, when you standardize and you get these z-scores, the units go away. So you have unitless data. And, okay? So it's important to know when we normalize. You normalize by standardizing, you normalize by putting the data between 0 and 1, that max mean. We talked about it earlier. Okay, so here we have, these are the dummy columns, right? Dummy variables. And for the fuel type that has diesel, CNG, and petrol, right? You have 3 dummy variables, but we only need to keep 2. So JUMP also can create this, right? All products basically can create this. Out of 1 categorical column, it can create 3 categorical columns. We keep 2, but they have numbers, right? Like 1 and 0. Okay. So whenever we have supervised learning, we separate the data into training, validation. If we want, we can have test data as well. All right. Usually, not usually, but you can choose to have 60% of your data. You have one file. 60% of the data will go into the training, 40% into validation. Right. And then we generate. So these are the variables. We'll generate, as you will see, this kind of an output for multiple linear regression. And okay, I want to go. All right. You see here, and we will see how this is generated. When you have when you here you have how many variables? 1, 2, 3, 4, 5, whatever. Let's say 12, right? You will come up with a model, a multiple linear regression model that will be negative 3608. Right, you see these coefficients. This will be produced by the software. Minus 123 times age. Okay. Minus 0.01 kilometers, minus 0.01 kilometers, and so forth. This is going to be, right, you keep getting the other numbers, this is going to be our multiple linear regression model, right? Since we are here, you see the p-value here that I mentioned? Yes, ma'am. See this p-value right here? And if you remember from statistics, behind the scenes, we will be doing hypothesis testing. Anytime you do hypothesis testing, alpha needs to be given. All right? So you take each one of these p-values and you compare it with alpha. If, right, if the p-value is less than or equal to alpha, this means, so here the input variable, right? This is the independent variables. Everything except this constant term is an independent variable. So this is not a variable, it's a constant. So these are the independent variables, all right? In any output that has a p-value, if the p-value is less than or equal to alpha, then this means that the independent variable is significant, meaning we want to keep it, right? So here, you take a look and you see this fuel type diesel. Remember, one of the things that we want to do is to eliminate variables which are not contributing, which are not significant. So this value here is extremely high. It's a lot higher than 0.05. That means we can get rid of this variable. And so are all of these guys right here. Now, at some point, even though you may have a variable which is not significant, people still may choose to keep them. But if we were to say remove the variables, remove the variables which are not significant, then we would remove every single one that has a p-value which is greater than alpha. So if p-value, right, if the p-value is greater than alpha, then, right, the independent variable is not significant. It means it does not help us in a significant, in a meaningful manner. This is very important. All right. So the software will provide that to us, will provide us with this output. Okay, so it's very important to know the predictors. It's very important to know the dependent variable or output variable, the variable we are trying to predict. We will also calculate these metrics like RMS error, okay, the average error for training data and for validation data. If we have test data, we can do that too. And traditionally, the error messages for validation, these error metrics, for validation data will be higher than the error messages for training. If they are consistently close, then we may have a very good algorithm. You see the error here is almost 0. The average error theoretically should be 0, but in the validation, right, it's quite high. That's expected. The sum of the square errors should be higher here. So this is what it is, 1, 2, 3. These figures for the validation data should be higher. All right? And then we will have, so here's the actual, the predicted will be generated, and the residuals are right here. There's a whole field in residual analysis. I hope that we will have time. Normally we don't, for me to do residual analysis because this is something that is very, very helpful. But here you have the actual and the predicted, and the residual is actual minus predicted. All right? Now one of the things that we can do with residuals, we can generate box plots, and we can see the distribution, and we can see if we have skewness or not. We will be doing that. And I will show you how the predictive multiple linear regression goes above and beyond what the explanatory multiple linear regression does by having three or four different ways to eliminate insignificant predictors. You have what's called exhaustive search, which is you have 10, 11 predictors. Exhaustive means give me all the combinations of the predictors. One model can have just one predictor, another can have 2, another can have 3, another can have 4, another can have 5, right? And you can compare them and find the one that give you the smallest errors, and maybe go with that. Now, if the best one happens to be the one with the one predictor, that may not be useful at all. So at some point you got to use some judgment and go with something. So we in statistics we talk about R square, and especially in multiple linear regression, statistics, mathematics, linear algebra. I will talk a little bit about linear algebra, but not that much, are at the heart of everything data mining, analytics. We're not going to do too much of this, but if you want to become better, the more you want to get in depth with this, you can take these math courses and more statistics, probability, and you can do, I mean, if you love this field and you're here because assume you like it or you love it to a certain extent, you can just do amazing things, you know. So, all right. So R square is between 0 and 1. R square, when you have many independent variables, and let's just assume that we have linear regression, right? With that we have simple linear regression. You have two variables, one independent and one dependent. R squared, the higher R squared, the closer R squared is to 1, the closer the dots are to the line. So if the dots are on the line, what is R squared? 1. And the line could be down this way, the dots could be down this way. R squared is also 1 if the dots are on the line and the line going this way. I talked about R and R square earlier in the course. Did I? I think. Okay, R is between a -1 and 1. R is the correlation coefficient. R square is called the coefficient of determination. Coefficient of determination. All right? This is very important material. Statistics is the heart. Statistics, math, linear algebra is the heart of everything analytics. Okay? I very highly recommend that you become quantitatively stronger. Take a couple of classes in calculus, take a class in linear algebra, take another class in statistics or probability, and you strengthen yourself, you position yourself to do great things. Okay, now, what happens though when you are using R square? Where's my, okay. When you're using R square, and the number of predictors, right? So the number of predictors, as the number of predictors as the number of independent variables predictors, same thing, increases, right? There's a bias creeps in. The bias goes up. To minimize that bias, they created R square adjusted. Okay? This is done to minimize the bias. To minimize this bias. Right? Can this bias be eliminated? I don't think you can do this 100%. To minimize this bias, all right? In this formula, P is the number of independent variables. That's what they. I don't like that choice, but P is the number of independent variables. All right. So P is that number of independent variables. N is the sample size, and R square is the coefficient of determination. So this R square adjusted will always be less than R square. So R square adjusted is a conservative version of R square, all right? We'll talk about the forward, the backward, stepwise. Okay. Okay, I want to use the remaining time to quickly do a thorough review of multiple linear regression. Okay? So, this is a multiple linear regression model. And whenever I use the word model, it means it has the independent variables and it has the error. Why is the dependent variable? The constants before the independent variables are called slopes. Okay, beta 1, beta 2. And this is, whenever we work with the model comes from the population. So if I have all of Northeastern and Y is the GPA, and I want to find out factors that can be used to predict the GPA, X1 may be the number of hours worked, X2 may be the SAT score, X3, so all these X's are characteristics of somebody, characteristics that, or predictors of somebody's success in terms of doing well with the GPA. This random term is always there because this is a factor. There are certain things that cannot be predicted. Okay, feelings. confidence. All right, so that's always there. So a model needs to account for everything. That's why you have this. This is the multiple linear regression model. There's something called the multiple linear regression equation. Obviously, this is an equation too, but the model has the error. The multiple linear regression equation does not have the error. Okay? A question could be a multiple choice question. What is the difference between the multiple linear regression model and the multiple linear regression equation? The multiple linear regression model has the error term. This doesn't. Okay? Everything that I discuss in class, you are responsible for. And that's why you also have the videos. Okay. Now, from the sample data, you come up with the estimated multiple linear regression equation. Y hat equals B0 plus B1, X1, blah, blah, blah. Okay? And this can be produced by software. These constants, the B0, the B1, B2, in one of the, here, you see this? Here is the B0, B1 is negative 123, B2, B3, and so forth, right here. This will be given to you in the software output, or you can generate it. Don't worry about this picture. This is if I have two independent variables, then I'm in three-dimensional space. X1 and X2 are the independent variables. Y is the dependent variable. In two dimension, you have the line. In three dimension, when you're in three dimension, instead of a line, you have the plane. All right. So what I want to show you is, and I can show that to you. I have a data file, Butler Tracking Company, and this is the data. This is the data. And Mr. and Mrs. Butler own a tracking company, and they keep track of, for each driver, the miles traveled and the number of hours driven. So this first driver, she drove. They have many drivers, so they ask you to go and try to approximate the total daily travel time for the drivers. So this driver, you ask 10 drivers, she drove one day 100 miles, it took her 9.3 hours to do that. You see there's another driver here, he drove 100 miles, it took him 6.5. You look at the data and you say, what is happening here? Data, good data never lies unless it's manipulated. So here you have, they try to predict this. The item you try to predict is always Y. Okay? So the other variable, miles traveled, can be our independent variable. Now, on the here, I have a butler.jump. Okay. I also have a butler.spss. This is an SPSS file. I can also do it in Excel. Let me go and do one of them in jump. All right. So let's hope we're not going to have any issues. I have the IT people come here at midnight and at 5 a.m. to keep an eye on these computers. When I am on the phone, they know who I am before I say my name. I asked them to install, oh, it gave us an error, both versions 14 and 13. There you go. It jumped to 13 because something else. Oh, this stuff. All right, so this is the data. All right, I created this jump file, and I took the data from here, okay, and I have it right here. Now, when we know what we are trying to predict, it is supervised learning. When you are doing supervised learning, after you clean up the data, what is the first thing that you need to do? You need, well, when I say clean up the data, if you have a column like that categorical, like different types of diesel, you're going to make the dummy variables, that's what I'm talking, right? Cleaning up, pre-processing is to prepare the data. This data is okay. I only really need miles and travel time. All right. So the thing that I want to do in the beginning is I need to partition my data. So, can you see, this is small. Can you see this?
If you can make it bigger, that'd be
let me see if there is a way, but, view. I want to make it bigger. Oops. Let's see. View. I know there's a way because I did it, but I forget now. This is the same data as this. So I want to partition the data. And to partition the data, I have a document, by the way, that has all these steps with the Toyota file. You'll see this again. I click Analyze, Predictive, and Make Validation column. They should use a better term here. This should be called Make Partition column. Okay? And this comes up. This dialog box comes up. All right? And here, so it has total rows is 10. We have very small data set. I want you to see to get the idea. All right? Right here. Okay. Control Shift Plus. Oh, that works. There you go. I did Control Shift Plus. Sometimes this thing works, and sometimes it doesn't. All right. That's it. All right. So you come here. Okay. Now I want to display both at the same time. All right. By the way, I like to create long column names so that they are descriptive, travel time, miles. You can say miles traveled. All right. Now here, I can specify the name of the column. I'm going to call this partition, and for now, I'm going to call it partition Dimitrios, just so that you can see a new column here called partition Dimitrios, and you know. Okay, but you want to call it partition. I want 60% of the data, 0.6 to be in for the training, 0.4 and 0 for test. We don't have much data. All right. And then I'm going to click Formula Random, and you will see a new column here. Formula Random, poof, you see how? And so what it did, it created 1, 2, 3, 4, 5 rows for training, and 1, 2, is it 6? Like, anyways, it should be close to 60% of 10, and the other for validation. Okay, so you need to have the data partition. By the way, the file that I'm going to use next time is, there's a file here called under jump. Hold on. Okay, this file here is if you read your emails, I have told you where to go and read more about the what jump does and how it does it. This here, building better models with Jump Pro MLR, this has this is a whole chapter 4 that talks about how Jump does multiple linear regression. And I also emailed you a PDF file of another inside Jump. They have all the documentation you need. So if I go help, books, and see this fitting linear models? This is all about what we are doing. This is 500 pages. I'm not asking you to read the 500 pages, but you can go and find out the answers to all questions. If we're doing something and you need to read something about it, right? There you go. So this document right here, okay, this is all how Jump does things. So you can go and reference it. Okay? Okay, so how do I then do multiple linear regression? I'm here in Jump and I will click Analyze, Fit Model, Analyze Fit Model. Then it comes into this fit model and this driving assignment we don't need at all. So travel time is what we want to predict. That goes to Y. Then you see this. So before I look at, well, there is a validation here. Let me just exit. When I do analyze fit model, you see you have Y, weight, frequency, and by, right? Well, the minute I put travel time into Y, you get the validation column. So which column is used to do partition, and that is when I move this guy over here. And I only have one independent variable, and I put that here. Right? I have a document in on Blackboard that I'm going to go through next time. I think this is MLR with, this should be with Jump. There you go. That has, I'm going to go through this next time. So that's the document, you can print it out. Okay, so I was right here. Now, we will deal with this next time. Click Run. And here is the output, the Jump output. And by the way, yeah, I did Control-Shift+, see? And Control-Shift-, so that's how you can make them bigger. Now, we don't need everything from here. For now, I'm going to go to where it says Parameter Estimates. Okay? So if I look at Control-Shift++, see this? If I take this part here, snipping. If I take this part here, all right, I have one independent variable, so I'm doing simple linear regression. Simple linear regression, right? It's called simple because you only have one independent variable. The model is estimated by y hat See, this is y hat equals b0 plus b1x. This is called the estimated simple linear regression model. Okay, estimated simple linear regression model. Estimated simple linear regression model. All right? And so you have y hat equals 1.064 plus 0.075 times miles. Okay, times miles. So we did simple linear regression. Okay. Now, if I take, I'm going to be taking different parts from here, and I want to explain them. If I take this, the summary of it right here, so this r square, this is r square. This is r square. When you do simple linear regression, in simple linear regression, this r square adjusted is not that useful. So disregard. Some people can use it, but we'll just choose to disregard it. Just disregard this r square adjusted. Okay. This is the root mean squared error. Another way, so root mean squared error. Another way to say the same thing is root average square error. Okay. I don't like to throw abbreviations too many, but root mean square error, root mean squared error, okay, RASC, root average squared error, right? Average of responses, this is the average of the y, and they used 5 in the validation. Okay, but basically we're looking at this r square now. Okay, now all right, we have a lot of other things. We'll talk about many of them. You also have here this cross validation. This will be repeated next time. This cross validation right here. You see it has the training data and it has the validation data. We want r square to be as close to 1 as possible. Okay? And we want r square, to be greater than some number, and I will say 0.70 for our class. Where did that 0.70 come from? This is used a lot in books. So we will be looking very heavily at the validation data, all right, when we are calculating. Sometimes we will be looking at the training data, for mostly we will be calculating statistics or error metrics on the validation data, because those are more real life. Okay. if R square is less than 0.70, so let's say we are looking at the validation data only, okay? Then, right, the question is, how can we improve it, right? Then what we want to do, we want to add new independent variables, one at a time. Because if you add many independent variables at the same time, you will not know which one contributed to the increase of R square. One at a time, okay? Hoping that R square, right, will increase. Hoping that R square will increase. Now, I will guarantee that after you add the new R square will be at least the old. It will be the old R square or more. All right? The worst case scenario is that it will remain the same. Okay. Now, go back here, oops. So, actually in this case I did it with SPSS. SPSS came up with, this is doing it in SPSS. I don't want to overburden you with other things, with other software. Here the R square came out to be 0.664. But the idea is, and I'll talk about this next time, is that you want to increase R square, right? I'll talk more about it. You need to introduce a new independent variable. So you ask Mr. and Mrs. Butler, what do the truck drivers do? And they say, well, they deliver stuff, deliver milk, I don't know, something. So, let me, I can keep this, but I don't have to. I can redo it over again. It's a good idea to maybe do it over again. So let me right click and delete this, all right? And I will add a new column. So you can right click here and say insert column. This is the new column, and I'm going to put these values here. 4, 3, 4, 2, 2, 2, 3, 4, 3, 2. And I can double click here and I can change the name to number of deliveries. Okay? Click OK. To the left, in this pane, P-A-N-E, you have the columns, all right? Number of deliveries, I want this to be meaningful numeric, so if you double click, this is numeric nominal. I want to change this to numeric continuous and click OK. I want to have a blue triangle like that. This is for meaningful numerical, right? So now I have, and I can get rid of this, so I have two independent variables and I can do multiple linear regression. So let's partition the data by doing analyze, predictive, make, this should be called make partition column, make validation. I'm going to call this partition, just call it partition now. And again, I'm going to use 0.6, 0.4. I'm going to do an example where I'm going to use an actual number there. There are other ways to generate the partition column. I'm going to, let's just keep using this formula random, poof, right, partition. So now I have two independent variables. Okay? So, how to do multiple linear regression? Well, same steps. Analyze, predictive, analyze fit model, analyze fit model. You see, you get this extra help here. It tells you what you're trying to do. I mean, what the different things that you can do here are. Okay. You want to predict travel time. That is, and you can drag and drop. That is this, right? Is Y. Miles and delivery, you can highlight the two of them and you can put them here. And partition is your partition, right? They should have called this partition. Maybe they may have a very good reason for doing it. But all right. So now, next time, I will show you there's other options here. Remember the forward, backward, whatever. So for right now, the method used to produce the estimated multiple linear regression equation is called ordinary least squares or standard least squares. I can choose to keep this dialog open, and you will see what it does, and click run. So you click run, and you have this dialog box still open, all right? There's a million things that JMP does. It's really an amazing product, and as I'm talking to more colleagues, JMP has been used very heavily at MIT. Okay, MIT uses everything. Okay, and I was talking to a friend whose husband years ago, 10 years ago, was doing a master in aeronautical engineering, and they were working on many projects, and they were using JMP. So, okay, so here, you see these parameter estimates? We don't have enough data. That's why this is not enough data, and that's why these values were not really generated. But from this, so we really need a lot more data. So let me see if I, oops, if I Control C, just to have more data to make it a little bit more meaningful. I'm just copying and pasting. So let me delete this column. Oh, travel time. All right, whoops. I'm just making oh, all right. I'm making this up. So, 55. Okay, well, that's an outlier. Oh, missing data. Oh, leave it there. I'm making data up. All right, so we're not going to get decent output, but that's okay. So I do analyze fit model. I want to do the partition, analyze, predictive, make validation, and I have 40 records now. So let's say 0.6 here, 0.4. Let's do this. I make this 0.3 and 0.10, right? So this is my partition. I keep changing it so that you see that this is something that you can decide. And click this. All right, so my partition is right here. All right. So I have 40 records here, so hopefully this will allow me. Now then, to do the regression, analyze, fit model, and travel time goes here, miles and number of deliveries go here, my partition goes into validation, all right, and I click run. Up, keep this open, I click run. Okay, so I got, you see I was lacking data, and still 4 is not too much, but I got something more meaningful. All right. Now, I will cover a lot of other parts next time. In the red, anytime you see a red triangle, go there and there are options, all right? Other options. Now here, if you go to the parameter estimates, you see this guy right here? So from this, you see now under cross-validation, I have training, validation, and test. This does not make sense, R squared to be negative. Maybe the data, that, it should not happen, I don't know why. But you, R square, what was the R square before? I forgot in the beginning what we had. But now we got, it's still, let me ignore this as well. You have an R square here, 0.41, and you have it down here as well. Oops. Oh, here. So let me just, we'll talk about this next time and what this means. From here, right, you get the estimated multiple linear regression equation, right? And this is y hat equals 1.48 minus, not minus, plus 0.025 times miles, and then plus 0.828 times number of deliveries. Looking at this model, which independent variable is contributing more towards understanding how the time is used by the drivers? I'm sorry? The intercept is a constant. You look, which of these two independent variables, miles or number of deliveries, is more important?
Number of deliveries.
Why?
Because there's a higher.
The number, right? In front of it. So this is just based on data. Now, if I go to the cross-validation, right, you have an R square for the training data. That should not be, maybe it's the missing values. I mean, this should not be negative values. And R squared, I don't have good data there. So this should not be negative. This here is the root mean square error, okay? And you see the validation has a much higher, as it should be. So, anyways, the you have seen though, the idea is that the R square now should be higher than before, but I put in bad data, and so it's not a good comparison between this R square and the previous R square, because initially I didn't have 40 records, I had 10, and the R square for that was based on the 10. The R square here is based on the 40. So, we don't have much time. I want to give you your test back. Please submit your homeworks.